My name is Boyang. I'm from Illinois Institute of Technology. Today, I'm gonna present encoding for reinforcement learning-driven scheduling. This is the outline of my today's presentation. Reinforcement learning is an area of machine learning that is primarily focused on dynamic decision-making, where an intelligent agent takes actions in an environment with the goal of maximizing some reward. And the recent studies have explored reinforcement learning for cluster scheduling with encouraging results. In reinforcement learning-driven scheduling, the agent is trained to learn a proper scheduling policy according to a specific scheduling objective, for example, reward, provided by system managers. Once trained, the agent can automatically interact with the scheduling environment and dynamically adjust its policy as workload changes. And this figure shows an overview of a typical reinforcement learning-driven scheduling. In this figure, each system resource is represented by a circle. The circles sharing the same color indicate these system resources are allocated to the same running job. Blank circles mean free system resources. At each step, state is observed and fed to the scheduling agent, and the agent provides job selection and receives the reward as the feedback. It is obvious that state representation plays a critical role in reinforcement learning-driven scheduling. In the following representation, I will use the phrase of state encoding and state representation interchangeably. Existing state representation models can be broadly divided into two classes: image-based state representation and vector-based state representation. Image-based state representation typically represents the waiting job information and the resource information in the form by a fixed access to the image, one dimension for resource availability, and the other dimension for time duration. The image for the first several waiting jobs are maintained for constraining the action space. And for the vector-based state representation, the waiting job information and the resource information are represented by vectors and concatenated into a fixed set vector as the input to the neural network. The first several jobs in the waiting queue are encoded for constraining the action space, and each resource is also encoded as a vector. However, there are still several open issues left for both of the encoding methods. For image-based state encoding methods, there are two major limitations. First, for HPC scheduling, although system resource has a fixed size, time duration could be infinite, as a job may take seconds to days or even weeks to complete. As such, image-based state representation cannot effectively address the wide range of or even infinite time duration issue. Second, while image-based representation can capture resource requirement per job, it lacks the encoding of job information such as job priority or job wait time. In order to overcome the aforementioned issues of image-based encoding, vector-based encoding is widely adopted, but they lead to a huge state space. So a scalability concern arises. This figure shows the cost exponentially increases with growing system size. So a scalable and efficient state encoding approach is essential. To address these encoding issues, we propose SAM model. This figure shows the SAM design. It encodes waiting jobs and the system resources as vectors and concatenates them into a fixed size vector input to the agent. Rather than encoding each system resource individually as a vector, SAM encodes the system resources through the viewpoint of running jobs. This means instead of encoding each node into a vector, we encode the nodes belonging to the same running job into a vector. We represent system resources by a concatenated vector of the resources used by a fixed number of running jobs. And this design is based on the two key observations. First, the resources belonging to the same job have the same system status. For example, the same start and end time. Second, parallel jobs occupying multiple computing resources are common in HPC. So the number of running jobs is significantly less than the amount of system resources. To validate this assumption, we analyze a number of workload traces from production supercomputers. And this figure plots the cumulative distribution function of the number of running jobs. For example, while Theta has 4,360 computer nodes for default queue, the number of running jobs is no more than 32. This suggests if we can succeed to encode the system states in the viewpoint of running jobs, the state input size will be significantly reduced. Now let me introduce SAM encoding design in detail. SAM encoding the scheduling environment by capturing the state of both waiting job and the system resources. In our investigation, we found that for a large system, like containing thousands of nodes, the training cost increase of waiting job information is negligible compared to the encoding of system resources. So we just follow the vector encoding. That is, encode first several jobs in the waiting queue. And for the encoding of system resources, we separate the system resources into two groups. The resources occupied by the running jobs and the idle resources. And we encode the occupied resources in the viewpoint of running jobs. And in this work, we express job size with the percentage of system size. So the idle resources can be expressed as 1 minus the total percentage of running jobs. So it is a redundant feature and we do not encode it. Since SAM encodes system states in the viewpoint of running jobs, the state input size will be significantly reduced. There is still a question left. Because reinforcement learning agent requires a fixed size input, while the number of running jobs dynamically changes. Then how many running jobs should be encoded for representing the system state? To attack this issue, we propose two methods. Note that production supercomputers can be broadly classified as systems with minimum job size requirement and the systems without such a requirement. For the former systems, we propose a method named zero padding. And for the latter, K largest job method is proposed. Now I introduce zero padding method for systems with minimum job size requirement. The idea is simple. In this method, we set K to the maximum number of running jobs, which is calculated by dividing the system size over the minimum job size requirement. This number reflects the maximum number of concurrent running jobs on the system. When the number of existing running jobs is less than K, we pad the rest of the vectors with zeros. And for the systems without minimum job size requirement, K largest job method is introduced. In such systems, it's likely the number of running jobs is larger than the K set by the administrator. Then how do we deal with this scenario? In other fields, such as natural language processing and computer vision, for variable size inputs, there are several methods to preserve the important information. However, encoding for reinforcement learning-driven scheduling, is different from that in the problems in natural language processing or computer vision. In natural language processing or computer vision, we cannot tell what information is important in advance. Fortunately, we can in reinforcement learning-driven scheduling. With respect to resource allocation, a large-sized job weighs more than a small-sized job because the large-sized job requires a large amount of the system resources. So when the number of running jobs is greater than K, SAM chooses to use the K largest jobs for encoding the system resources. K can be chosen by the administrator through experience or trace analysis. Since we claim that K-largest job method can preserve important system state information, we want to validate this claim. First, we examine the percentage of total node hour loss for each workload. And the table shows the amount of node hour losses by using different K values. It clearly indicates that total node hour loss percentage is extremely small, within 1.3%, no matter when K is set to 30, 40, or 50 for both logs. We also want to ensure that the K largest job method can cover the majority of resources nearly all the time. The bottom figure shows the amount of trace periods that is covered by using different K values. Two plots are presented here. Left one for covering 90% of the allocated nodes, and the right one for 95%. And we can see that the worst case is when K is set to 30 for data star workload. Even in such case, out of the 13 months, it covers 90% of the allocated nodes for about 97% of the time, and covers 95% of the allocated nodes for about 93% of the time. For the other cases, it will cover more than 95% of the allocated nodes, more than 99% of the periods. So put them together, this clearly demonstrates that we can encode K largest running jobs to represent the system state with negligible information loss. And now let me talk about the experiment setup. We implement SAM in the event-driven scheduling simulator CQSIM and use it in our evaluation. We use two workload traces, theater and data star, for evaluation. They are chosen to represent two HPC systems. Theater stands for the computing systems with minimum job size of 128 nodes. And the data star represents the computing systems with no minimum job size requirement. For each trace, 60,000 jobs are used for training, 1,200 jobs are for validation, and 6,000 jobs for inference testing. During training, we monitor the convergence rate by taking a snapshot of the model after each episode. And each episode consists of 600 jobs, so there are total 100 episodes. And in this study, we compare SAM with the vector-based encoding deployed in JS with policy gradient method. And for other information, such as reward setting, neural network configuration, I will not present here due to time limit, but you can refer to the paper for detail. And next, I will present the experimental results of comparing SAM with JS. Our analysis centers upon 4 questions. First, does SAM lead to a faster convergence rate for training reinforcement learning agent? Second, does SAM lead to comparable scheduling performance? Third, how much are reinforcement learning agent training and inference costs when adopting SAM? The fourth is how scalable is SAM enabled reinforcement learning driven scheduling? And this figure shows the convergence rate of reinforcement learning agent using different state encodings. It clearly shows that SAM leads to a faster convergence. And we attribute this to the reason that SAM results in a much smaller sized neural network. And this figure presents the overall scheduling performance obtained by SAM and JSSPP state representations with KVH graphs. We use node utilization, the reciprocals of average job wait time, maximum job wait time, and average job slowdown in the plots. All metrics are normalized within the range of 1. 1 means a method achieves the best performance among all methods. For all metrics, the larger the area is, the better the overall performance is. We observe that the KVH graphs of SAM and JSSPP almost overlap, both on theta and the data star. On theta, SAM performs slightly better than JSSPP in utilization, maximum job wait time, average job wait time, while JSSPP performs a little better in average job slowdown. The difference of all these metrics are within 4%. On data star, the difference of all these metrics are within 6%. In a further investigation, we found that wait time and slowdown for most of the jobs are similar. The results demonstrate that SAM can achieve comparable scheduling performance. And we also evaluate the training and the inference time costs of reinforcement learning agents by using different state encodings. The training time is the time cost of training 60,000 jobs, and the inference time is the time cost of testing 6,000 jobs. This figure shows that the training and the inference time comparison, and the training and the inference speed up can be up to 9 times and 6 times separately. This clearly shows SAM has a much faster training and inference speed up than JSSPP. And in this set of experiments, we examine training and inference time when increasing system size by using different state encodings. In this figure, system size is increased from 4,360 to 34,880. As system size increases, the number of jobs and the vector input also grow proportionally in this experiment. The plots show that the training and the inference time of SAM increases very slowly, while the training and the inference time of comparison method increases drastically with the system size increasing. When the system size is set to 34,880, more than 1,000x improvement is achieved. In this work, our contributions are summarized as below. First, we propose a scalable and efficient state encoding method called SAM. Second, 2 methods are presented to encode the environment into a fixed size vector, that is zero padding and k largest job method. Third, SAM can lead to dramatic training and the inference time reduction while maintaining comparable scheduling information. Thanks very much. Any question?
Thank you.
I do have a question. Do you have an example of what you use the simulator for, and what outcomes you? Because this is a method to allow you to simulate faster by changing the representation, right? But what are you using the simulator now for? Sorry if you already gave more details on that, but I may have missed that.
The simulator I use is a SQL Sim, so it's an event-driven simulator. And we replaced the scheduling before it used the heuristic scheduling algorithm, and we replaced that part with reinforcement learning scheduling algorithm. So you can refer to my paper for the link. I think I list the link in the reference part.
Okay, thank you.
Yeah, so let me also add a comments to the question. So yeah, I'm also a co-author of this paper. So on the chat, I gave the link to this simulator. This is a simulator, it's an open source simulator. And then this simulator has been used for over 10 years. We started this simulator, that's actually 10 years ago. And then at that time, we realized there's no open source simulator for scheduling. And then the student developed this tool, this simulator, and we did a comparison of a number of testing of this tool with the tool from this from the group. I think from this parallel. Remember, so everyone probably use this parallel workload archive. And yeah, we compare our tool with their tool, but we ask to keep their tool private. And the goal for us to compare these two tools is try to, well, it's hard to have two simulators actually end up exact same event trace or exact same order, but it's able for us to evaluate such as what are the, when you give a different traces, where you're able to end up, let's say all of you going to use the first come, first serve with easy backfilling. Then let's see, we have this trace feed into both simulator, and then we will look into what the result of these two simulator in terms of resource utilization, make span, job waiting time, and the response time, bounded slowdown, a number of factors. We can kind of draw a curve to compare two simulator. At that time, we verified that these two simulators end up with the same result. So that's why we have been using this tool, simulator tool, for a number of years. Anyway, so I encourage everyone to use this, to take a look at the tool. It's open source. We are trying to expand this tool as much as we can.
Sorry.
Thank you.
Last year, we've prepared a sub-page on the JSSPP webpage where we keep links to various tools and simulators. Is it okay if we add this link to the JSSPP webpage so that it's somehow kept forever?
Yes, that would be great. Thank you.
Oh, yeah, sure. You're welcome. I noticed that, I'm sorry, I came a little later. I missed the start of the talk, but I noticed that you are using DataStar and Atlas traces. Those are the ones that you can find in Parallel Workloads Archive, or those are some different traces with the same name?
You can find it. Go ahead, Professor.
Yeah, so yeah, DataStar can be found on the Parallel Workload Archive, and then Theta Log, all the ALCF Argonne Leadership Computing Facility. All the traces from ALCF is already online. So I'm going to put on the chat. Their workload trace is online. So I'm going to send the link on the chat. Give me a minute, okay?
Excellent. And just in case I'm not sure whether these links are in the paper. I believe they are, but if not,
yeah.
So please feel free to add the links to the traces to the paper, because it's always great to have them in. Thanks.